Lesson 7.2, going to talk about matrix algebra. We've talked about matrices in the past, but just like every other topic this year, now we're going to go a little more in depth with it. So in this lesson, we're going to talk about matrices, how to add and subtract, multiply matrices, identify the identity and inverse matrices, determine the determinant of a square matrix, and then apply it to a few application problems. Okay? Just like we talked in lesson 7.1, solving systems of equations, you can use a matrix to solve the systems of equations as well. First, we need to talk about some terminology. The definition of a matrix. M and N represent the rows and the columns of the matrix. M refers to the rows, N refers to the columns. We say, if we're trying to identify a matrix, an M by N matrix. Tells us how many rows and how many columns. Okay, the shorthand notation, they use A with the subscripts IJ, I referring to the entry in a row, J referring to the entry in a column. Okay. Some more vocabulary. So each value within the matrix itself is called an element or an entry. Okay, we classify it A sub IJ, I referring to what row that entry is in, J referring to which column that entry is in. If we're going to talk about the order of an M by N matrix, we just write M by N. That tells us how many rows and how many columns that matrix has. So if we wanted to determine the order of the following matrix, we simply want to write determine how many rows there are, how many columns there are. If we look, there's 2 rows. So we have a 2 by, and then we have 1, 2, 3 columns. So this would be a 2 by 3 matrix. That is referring to the order of that matrix. Next, we're going to talk about matrix addition and subtraction. Pretty straightforward. If we're trying to add 2 matrices together, find the sum, all we have to do is add corresponding entries together. If we're going to find the difference between 2 matrices, subtract them, all we have to do is subtract corresponding entries. Okay, one thing that has to be true, if we're going to add or subtract 2 matrices together, they have to have the same order, meaning they have to have the same number of rows and the same number of columns. So in this example, we want to add the 2 matrices together. If we look, they have the same order. They are both a 2 by 3 matrix. So all we have to do to find the sum is add corresponding entries together. So this will be equal to, if we're looking for that first entry, 1 plus 2 would give us 3. And then we go to the next entry, 2 plus 3 would give us 5. 3 plus 4, 7. 4 plus 5, 9. 5 plus 6, 11. And 6 plus 7, 13. So adding or subtracting 2 matrices, pretty straightforward. Next, we're going to look at scalar multiplication for matrices. Basically, if we have a scalar, that means it's just a coefficient multiplied in front of the matrix. So essentially, all you have to do is distribute, in this case, that 3 to each entry in the matrix. So this would be equal to, multiplying the 3 by each entry, we'd get 3, 6, 9, 12, 15, and then 18. So this is called scalar multiplication. You can think of it as a coefficient in front of a variable, just being multiplied, have to multiply it through to each entry. 2 special types of matrices we're going to talk about, the zero matrix and additive inverse. First, the zero matrix is an M by N matrix where each entry is equal to 0. Okay, pretty straightforward. Zero matrix, each entry is 0. The additive inverse, if we have a matrix A consisting of M by N rows and columns, well, the additive inverse would be a matrix B that has the same order, an M by N matrix, where if we added each entry from matrix B to matrix A, our result, the sum, would be the zero matrix. Okay, so each entry in matrix B would be the additive inverse of matrix A. For instance, if our first entry in matrix A was 2, the additive inverse for matrix B would have to be negative 2. Because if we added those two together, the result would be 0. Now we're going to talk about matrix multiplication. This tends to be a little more confusing than matrix addition or subtraction or scalar multiplication. Okay, it's not as straightforward. So suppose we have matrix A with an order of m by r, and matrix B that has an order r by n. Okay, so one thing we have to be aware of, if we're going to multiply two matrices together, the number of columns in the first matrix must be equal to the number of rows in the second matrix. Okay, those always have to be the same value. The order or dimensions of our product will be the rows of our first matrix and the columns of our second matrix. Okay, so something you have to be aware of. If we're even going to multiply two matrices together, the columns of the first have to equal the rows of the second matrix. Okay, and then the rows of our first combined with the columns of the second, that will be the order of the product. So we want to find the product of AB if possible. So if we look at matrix A, we have a 2 by 3 matrix. And if we look at matrix B, we have a 3 by 2 matrix. Okay, so looking at the column of the first matrix and the row of the second matrix, those values are the same. So this matrix is defined. Okay, if we say a matrix is defined, that simply means that we can multiply that matrix out to get a product. Now we need to look at the rows of the first matrix and the columns of the second. That tells us the dimensions of the product. So our end result will be a 2 by 2 matrix. So if we're going to multiply this out, first we have to take row 1 of our first matrix and multiply it by column 1 of the second matrix. So we're going to look, we have 3 entries in row 1 and 3 entries in column 1. So we're going to multiply each of these entries together. We're going to take 1 times 1 plus 2 times 2, which is 4, plus 3 times 0, which would just be 0. Now we're going to take row 1 and multiply it by column 2. We're going to take 1 times 0, which would be 0, plus 2 times 1, which would be 2, plus 3 times negative 1, which would give us negative 3. Now we're going to go to row 2, multiply by column 1. 0 times 1 gives us 0, plus 1 times 2 gives us 2. Negative 1 times 0 would be 0. Finally, we're going to find our last entry. Row 2 times column 2, 0 times 0 gives us 0, plus 1 times 1, 1. Negative 1 times negative 1 gives us a positive 1 as well. Now if we simplify each of these entries, 1 plus 4 gives us 5, 2 minus 3, negative 1, 0 plus 2 plus 0, 2, 1 plus 1 gives us 2. So this would be the product of AB. So first we had to determine if this matrix was even defined. We did that because the columns of the first equal the rows of the second matrix. We looked at the rows of the first matrix, which was 2, the columns of the second matrix, which was 2. That gave us the dimensions of our product, multiplied using the rules for matrix multiplication, and got our end result. The identity matrix is a square matrix, meaning the rows and columns must be the same dimensions. Okay? And the identity matrix has values of 1 along the main diagonal. The main diagonal simply starting in the upper left, going diagonally down to the bottom right. All those entries are going to be 1s. Every other entry is going to be a 0. This is called the identity matrix. The reason the identity matrix is important is it allows us to find the inverse of a square matrix. So if we have a matrix A with order n by n, it's a square matrix. If there is a matrix B such that if we multiply A times B, or if we take B times A, if that result is equal to the identity matrix, which we just talked about, then B is the inverse of matrix A. Okay. The way to denote that B is the inverse, A raised to the -1, okay, that -1 referring to the inverse. Now we're going to discuss how to find the inverse of a 2 by 2 matrix. So if we have a matrix A, B, C, D, and we want to find the inverse of that matrix, what we have to do is take 1 divided by, multiply A times D, and subtract B times C. And then we're going to switch the places of our entries A and D around, and then change the sign on our B and C entries. Okay, and then if we would multiply that scalar through to each entry, that would give us our inverse matrix. Before we go through an example of finding the inverse of a matrix, first we need to discuss the determinant of a square matrix. So if we have a matrix A with entries A, B, C, D, this is a square matrix. If we want to find the determinant of matrix A, which, using notation, if we put the absolute value symbols around the entries, okay, that denotes that we're talking about the determinant. All we have to do is multiply A times D, our entries along the main diagonal, and subtract the entries going across our other diagonal, BC. So that's how you find the determinant of a matrix. Multiply A times D along the main diagonal, and subtract B times C. Now that we know what the determinant of a matrix is, we can go through an example of finding the inverse of a matrix. So if we have an n by n, a square matrix, that matrix only has an inverse if the determinant of the matrix is not equal to 0. So the process of finding an inverse, first we need to find the determinant of that matrix. So the determinant of matrix A in this example would be equal to 5 times 3 minus 1 times 8. 5 times 3 is 15. 15 minus 8 gives us 7. So since the determinant of matrix A is not equal to 0, we can find the inverse of this matrix. So to find the inverse of this 2 by 2 matrix, which we denote by A raised to the -1 standing for the inverse matrix, that is going to be equal to 1 divided by the determinant of matrix A, which we just found, which is 7. We have to switch our A and D entries, so our 5 and 3 are going to switch positions. So this becomes a 3, this becomes a 5. B and C, those entries change signs, so this is going to become a -1, and this becomes a -8. Now if we multiply using scalar multiplication, 1/7 times 3, we get 3/7, -1/7, -8/7, and 5/7. So this would be our inverse matrix. If we took our original matrix A, multiplied it by this inverse matrix, our result, our product, would be the identity matrix. To end this lesson, we're going to talk about some basic properties of matrices. So if we let matrix A, B, and C be matrices whose orders or dimensions are such that the following sums, differences, and products are defined. First, we're going to talk about the commutative property, which you've heard in the past as the commutative property. For addition, it doesn't matter if you take matrix A plus matrix B, or if you take B plus A, you're still going to get the same sum. The commutative property for multiplication does not hold true. Okay, this is a key point, a key property that we have to remember. Commutative property for multiplication does not hold true for matrices. If you take matrix A times a matrix B, that is not necessarily going to be equal to matrix B times matrix A. The associative property, okay, the way we add or multiply matrices together does not matter. So if I would take the first two matrices, multiply them together, and then multiply that by a third matrix, it wouldn't matter if I first multiplied the last two matrices together. Okay, so that's the associative property, holds true for addition and multiplication. The identity property. For addition, if I take a matrix A, add the 0 matrix to it, we're still going to have matrix A. For multiplication, we have to talk about the identity matrix, which was the matrix that had 1s along the main diagonal and 0s in all the other entries. If we take a matrix A times the identity matrix, we're still going to get matrix A back. Okay, so those are the identity properties. The last two properties, the inverse and distributive, okay, pretty straightforward. We talked about the inverse properties. For multiplication, we take a matrix A times its inverse matrix. Our result is going to be the identity matrix. Distributive property, what we've always talked about in algebra, if you take a matrix A times the quantity of B plus C, all you have to do is take matrix A times B plus matrix A times C. I'm going to end by going through a few extra examples. Okay, you can stick around, watch these, give you a better understanding of how to do these basic operations with matrices. So in the first one, we're going to talk about matrix subtraction. Okay, we did a problem where we added two matrices. Now we're going to subtract two matrices. Pretty straightforward still. All we have to do is look at corresponding entries and subtract those values. So for the first entry, we have 6 minus 8 would be negative 2. Negative 1 minus a negative 2. So if we're subtracting a negative, we can think of that as addition. So negative 1 plus 2 would be a positive 1. 2 minus 5, negative 3. And 4 minus a negative 3, again, think of this as addition. 4 plus 3 would give us 7. So first thing, both these matrices had to have the same order. They had to have the same dimension. That always has to be true if you're going to add or subtract two matrices. They must have the same dimensions. Both of these were 2 by 2, so we could do that. Subtract corresponding entries to get our difference. The last example we're going to discuss is another one of matrix multiplication. So a matrix A, which is a 3 by 2 matrix, and matrix B, which is a 2 by 2 matrix. So first we have to look at the columns of the first, the rows of the second. Those need to be the same value if this matrix is going to be defined, meaning we can find the product, we can multiply them together. They are, so we can multiply these together. The rows of the first and the columns of the second, those tell us what the dimensions of our product are going to be. So we're going to end up with a 3 by 2 matrix. So if we're taking the product of AB, first we have to take row 1 times column 1. So we're taking 2 times 3 to get 6. 3 times 1, so plus 3. Then we can go to column 2. So we have 2 times negative 2, we get negative 4. 3 times 5, we get plus 15. Now we got to go to row 2, column 1. So we have 4 times 3, we get 12. 5 times 1 plus 5. Move over to column 2. 4 times negative 2, negative 8. 5 times 5 plus 25. Now we finally move to row 3 and column 1. 6 times 3, we get 18. 7 times 1 plus 7. Now we're going to move to column 2. So 6 times negative 2, we get negative 12. 7 times 5 plus 35. Now we just need to simplify each of these entries. 6 plus 3, we get 9. Negative 4 plus 15, we get 11. 12 plus 5, 17. Negative 8 plus 25 would be 17. 18 plus 7, we get 25. And negative 12 plus 35, we would get 23. So, multiplying matrix A by matrix B, first we have to make sure the matrix is defined, meaning the columns of the first and the rows of the second are the same value. Then we can look at the rows of the first, columns of the second. 3 by 2 tells us the dimensions of our product. Multiply them together using our rules for matrix multiplication, and we get our product.